So, chemists got to be different. Chemists have a particular way of identifying salts that are not like what everybody else thinks about identifying salts. So we're going to learn that now. Yeah. Okay, so salts are the product, other than water, of an areneous acid reacting with an areneous base. So let's see, the strong acid we used in our lab Tuesday was hydrochloric acid. And if we react hydrochloric acid with the base that we used in the lab, this then is one of the 5 major classifications of chemical reactions. Okay, you need to remember how to classify reactions. Okay, I have an acid and I have an ionic compound here, and you treat acids like ionic compounds anyway, like when you're naming and use them like this. That means this is a 2-part compound and this is a 2-part compound. And these two 2-part compounds switch partners, keeping the guys with the girls. Okay, so the guys go with the girls and the guys go with the girls, not the other way around. All right. So the H goes with the back part of this, which is the OH. And the K goes with the back part of this, which is the Cl. Now, typically you balance the formula, but potassium has a 1+ charge, and chlorine in a binary compound has a 1- charge, so it is already balanced. So now we have that sub-classification that you need to know about and need to be able to recognize. The sub-classification of double replacement reactions, and that's an acid-base reaction. That's what this whole unit's about, acid-base. Got it? Okay? So this is an acid-base reaction using the double replacement form, the way that we learned to do it back in Unit 5. Got it? Okay? Now this is an areneous acid because it has an acidic hydrogen on the front. An areneous acid has to be able to give away a hydrogen ion. So there has to be a hydrogen in there somewhere that can be given away. And not all formulas that have hydrogen will give them away. Hydrogens that are attached to non-metals aren't given away. Hydrogens that are attached to non-metals are not given away. So all those organic compounds with all those hydrogens in there, the ones that are attached to the carbons aren't given away. Okay? Ammonia, NH3. The nitrogen is not is a non-metal. It's not a metal. So the hydrogen won't be given away from the ammonia, typically. All right? Now that's assuming we don't create something with it. Sometimes we do give them away, like with the hydronium we made previously. Here, this hydronium, that's got that extra hydrogen ion on it. So that hydrogen can be given away. But in the basic formula, when there's no charged particles here, you don't give them away. Does that make sense? The hydrogens have to be acidic hydrogens, the ones that are given away in solution. So, an Arrhenius acid, this is an Arrhenius base because it has a hydroxide that can be given away. Now, it has to be a hydroxide. There are OH groupings that are not hydroxides. In an organic compound, an OH grouping would be called an alcohol group. Okay? Those aren't given away in solution. All right? It's only the hydroxides that are attached to either a metal or some cation that are given away. So you have to have the hydrogen being able to be given away, the hydroxide be able to be given away to make these an Arrhenius acid and an Arrhenius base. So once you have an Arrhenius acid and Arrhenius base, the product other than water is a salt. Well, that's water, so that's not a salt, because we said other than water. That makes this the salt. The potassium chloride is a salt. And anything you can form, you don't have to form it that way, but if it can be formed through an Arrhenius acid-base reaction other than water, that's a salt. That's the definition of a salt to a chemist. Does that make sense? All right. All right? That's for you to do now. Oh, by the way, not all salts should be sprinkled on your food. Magnesium sulfate is a salt. You buy it in the store. It's called Epsom salts. Don't sprinkle that on your food. Huh? Yeah, if you're constipated, you can. So what does that tell you? You can digest it, but you don't know what constipation is, right? What do you take to relieve constipation? Don't say it out loud. Okay? Well, if you eat enough magnesium sulfate, it's going to relieve your constipation.
What is rock salt then?
It's just less than, not as pure form of table salt. That's just in larger chunks. What you buy in the grocery store labeled as rock salt. That's what it is. It's just sodium chloride.
Just a larger version.
Mm-hmm. Kosher salt, all pickling salt. It's all the same stuff. Okay, everybody got it? Who needs more time? Nobody needs more time? Alrighty. So here's our acetic acid dissolved in water. And we're going to react it with potassium hydroxide. And so now we're going to write using the double replacement form that we used back when we were Unit 5. The hydrogen ion just joins up with the back of this, which is the hydroxide ion. We get HOH or H2O. And the potassium, the front of this, joins up with the back of this, and the back of this is the acetate ion. We need to be careful to make sure we balance the formulas. Well, hydrogen was 1 plus, hydroxide was 1 negative. That's balanced. Potassium is 1 plus, and acetate is 1 negative, so that's balanced. So the salt is going to be the species other than water formed from this areneous acid and areneous base. And that would be this. Potassium acetate is the salt. Okay? How'd you do? Got it? All right. I want to identify a term for you. Amphoteric.
Is that an ER after the T?
Yeah, TERIC. All right, it's a substance that can act as both an acid and a base. And so in our acid dissociation equations, in Bronsted-Lowry form, when we pulled the proton off of the acid and stuck it on a water, water was acting like a base. Under different circumstances, water can act as an acid. Okay? Any questions? So that's just a definition. You need to know the definition. Okay? Amphoteric. All right. Now, you have to be able to recognize by sight strong acids. So you've already learned to write the formulas from the names. We did that back in Unit 5. So if I give you the name of an acid, and ask you if it's a strong acid or a weak acid, well, the first thing you need to do is convert that to a formula to be able to tell using the rules I'm going to give you. Okay? Now, if you can do it mentally, fabulous. If you can't do it mentally, do it on paper. Okay? You know, there's a reason why we were given these nice writing instruments and these things to write on. We actually should use them if what's up we need to be able to answer questions. Okay? I'm being sarcastic. Nobody's laughing. Okay. So I want to classify acids in two forms to give you a set of rules. You can memorize the strong acids if you like to memorize stuff. But I'll give you two simple rules for recognizing strong acids if you prefer to do that. Okay? I like to do the classifying them and recognizing them by rule rather than recognizing them by actual formula. Because by recognizing them by rule, I can actually identify even more strong acids than the ones you have to know for this class. Okay? So the first classification is binary. And I hope everybody remembers what binary means. What's a binary compound? Two what? Two different elements. Not two atoms, two elements. Okay? So you got the binary acid classification, then we have the oxyacid classification. All right, now the strong binary acids have acid anions formed from the middle halogens. What are the halogens? Jason, what are the halogens? If I have a periodic table, how do I find them? Get out your notes for Unit 2 and figure it out then. I don't know. Usually it's just an excuse for not wanting to try. And I don't let you not try. You got your notes from Unit 2? Jason, I want to see you after class, okay? You hear me? Huh? Okay, Grace. What are the halogens? How do we find them? Next to the last column on the right. So if I were looking at that and I was saying, well, what's the middle halogens? What am I think? What would you think that is? Not the last column. She said it was the next to the last column.
Well, then the ones in the middle.
Well, which one are those? Acetate. Okay. Chlorine, bromine, iodine. Okay. So any acid with one of those as an anion, that would be HCl, HI, and HBr. I didn't write them in order. Okay. Any of those three. Those are the strong binary acid. Any other binary acid is going to be weak. Okay? Makes it pretty simple. See, the stronger it's weak, those are the only strong ones. Okay? Now, the simple rule for strong oxyacids is these have, the strong oxyacids have oxygens outnumbering acidic hydrogens by, but by at least 2. Oxygens outnumbering acidic hydrogens by at least 2. All right? So Avery, do the oxygens outnumber the hydrogens in this formula? Huh? By how much? Okay, is that a strong acid? Yes. That's not so hard, is it? Miranda? Do the oxygens outnumber the hydrogens? By how much? So it's more than 2. Is it a strong acid? Yep, by at least 2. And since 3 is more than 2, then it meets the requirement. Is this a strong acid? Okay, there you go. All right. Anything that contains oxygen in the anion. The anion is sort of like the back side of the formula. The protons are positive. The rest of it's got to be some kind of negative charge. Okay. Gabriel, do the oxygens outnumber the hydrogens?
Yes.
By how much?
2.
By 2. Is it a strong acid?
Yes.
Yeah. Brooke, do the oxygens outnumber the hydrogens? Is it a strong acid? How much do they? How much does the? Let's see. By how much does the oxygen outnumber the hydrogens? By 2. So it meets our requirement. So those are the acids you have to know by sight as being strong. You can either memorize them, or you can just say, well, I know there's 2 rules. I can do it. No problem. I like the rules personally. Okay? If you don't like the rules, okay, fine. Do whatever works for you. Got that? Any questions so far? All right. We're getting close to getting to the stuff we're going to be doing on Monday. Monday's lab not only involves neutralization, it also involves stoichiometry. Yay! All right, now, with the PowerPoint I showed you the other day after the lab, I showed it to you the day after the lab, so it would have been yesterday. I think I showed you the last of the PowerPoint. We talked about the fact that acetic acid is one of the weak acids. Let me show you that formula here real quick. It's HCH3, CO2. Okay, now, here's the thing to remember. This is the anion. These hydrogens right here are attached to this carbon. They are not acidic. Okay? It's this hydrogen right here that's acidic. Okay? Now, if we were really smart, we were thinking back to when we were doing the organic chemicals, you would probably remember, well, let's just do the whole structure here. That we get, that's wrong. Doggone it. Even I messed it up. All right. I'm going to make a larger acid. I don't want to make propanoic acid. I want to make ethanoic acid here. Okay, so that's the actual structure of acetic acid. Okay? So this first hydrogen, when we write it like this, we're writing it like we're doing it somewhere between an organic acid formula and a physical acid formula. But we're putting the hydrogen on the front just to make it easier for us, okay? But this is the hydrogen that actually comes off in organic acid. The one that's attached to the oxygen, which is attached to the carbonyl. Okay? Remember all that? Those terms? Yes? Okay. So, this hydrogen is actually the one that removes itself, and it's not attached to a carbon. It's attached to an oxygen. So, if we break this up then, and let's use the Arrhenius system for this explanation to start with anyway. We're going to get a hydrogen ion and an acetate ion. Now, when I showed you that PowerPoint, I showed you that most of these molecules of acetic acid do not break up in water, at least not in the concentration we had in our solution on Tuesday. When you have you have to actually add base to it to get under ball breakup. Okay, when you just put acetic acid in water, most of the acetic acid or most of the hydrogen acetate molecules are not broken up. Only a few of them are broken up. A small percentage are broken up. Okay, that's what makes it a weak acid. Okay, well, there's even more to it than that. What happens is, in reality, is those that actually break up, even more of them continue to break up. But the reason why in the solution you only have a small number broken up is that these are also reforming the original stuff. So this thing is going around and around in a circle. Okay? Molecules of hydrogen acetate are breaking up and forming the hydrogen ion and the acetate ion. But there's also hydrogen ions and acetate ions that are banging into each other and forming a molecule. Okay, that's going on all the time. And you get a kind of a balance somewhere, and that balance is called the equilibrium. Okay? It's called the equilibrium when it's balanced. When all of this stuff isn't in this form, all of this stuff isn't in this form, but we're always making this stuff and making this stuff at the same time. Now, you can think of it like this. when the bell rings out here, well, let's just use round numbers rather than the actual numbers. Let's say we got 1,000 students on A wing where we are, and there's 1,000 students over on B wing. Okay, when the bell rings, everybody's going up and down the hallway, but the number of students on average stays the same on both hallways. Why is that? Because they're going back and forth. That's what's happening here. They're going back and forth. And if you had an imbalance in the number, because this number the number of these versus the number of these almost never completely balanced. Okay, you can think of it like this: that let's say on B wing over there, because they got that art stuff over there, they have 1,500 students, and over here we got 500. Okay, same number of students. I'm just saying that on average for this explanation, we got more students over there. The bell rings, the number stays about the same. It's about 1,500 students over here and about 500 over here, but we're constantly changing. You see? That's kind of like this right here, where here's our 1,500 students and here's our 500 students. You know what I'm saying? So that's just a balance, okay? But whenever you have this and it's like the bell is constantly ringing, okay? We never sit in class. We're always going up and down the hallway. That's what's happening with this kind of equilibrium. You got it? It never stops, all right? And that's why we call it a dynamic equilibrium. A system like this, and there are lots of different dynamic equilibriums. A system like this in chemistry is dynamic because it's constantly changing, but it's an equilibrium because the relative amounts don't ever change. Okay? Because just as much if it goes this way, there's a balancing amount that's going this way. Does that make sense? Yes? Okay. All right. So weak acids then do this. And this is kind of the basic idea behind this buffering effect we talked about with our weak acid yesterday. Why we have to put so much base in there to neutralize a weak acid compared to a strong acid. Okay, which seems almost counterintuitive. And I do that lab on purpose because it is counterintuitive. Most people think, well, if it's a strong acid, you got to have more base. That's not the way it works. I want you to think about acids in a different way. There's a huge difference between the concept of strength in an acid and concentration in an acid. Okay? Strength and concentration are two different concepts when we're talking about acids. Strength and concentration are two different things. Concentration is the amount of one substance dissolved in another. Strength, when we're talking about acids and bases both, refers to how completely the acid or base dissociates. Two different concepts. And up until this point in time, very few science teachers, in my experience, have told you that there is a difference. Okay? I've had students in honors classes that just couldn't understand why orange juice wasn't a weak acid all the time because of the pH. The pH has nothing to do with either strength, well, it has something to do with strength, has little to do with strength, has a lot, or concentration alone. They both have to come together to give you pH. Because pH is not about the concentration of the acid. pH and pOH are about the concentration of H plus in the Arrhenius system or theory or the concentration of H3O plus in the Bronsted-Lowry theory. Okay? You have to have both working at the same time, okay, to get this hydrogen ion concentration up and lower the pH. And pH is all about counting hydrogen ions. pH is all about counting hydrogen ions. Okay? In a sense. That's actually the amount per unit volume of whatever you're dissolving it in. So we identified earlier what the strong acids are. What makes something a strong acid? Okay, so here's our strong acid. Here's our strong acids. What makes it a strong acid? Strong acids dissociate. Okay. Okay, that's the difference. The strong acids don't have anything to do with the pH. Strong acids have to do with how much hydrogen ion or hydronium ion you get in a solution. Okay? So I can take a really, really tiny amount of hydrochloric acid, a strong acid, and put it in water, and I don't get a low pH. But I can take a lot of a weak acid and still not get a low pH. Because it's all about how many of those hydrogen ions or hydronium ions we get in the water. Let's see here. I wonder if I call any of the extra copies of that. I'll have to cut them. I have to cut one out. Let me stop the recording. No reason to have a long pause in the recording.